Okay, so in this next section, I'm just going to give the beginning overview part.
Yeah.
This is where we're getting a little more in depth, but we're going to talk about data wrangling, and we'll be using the tidyverse, which you should already have installed, and also Lubridate. So if you haven't installed Lubridate, is that in the tidyverse? No, I think it's separate.
It is, but you have to load it separately.
Okay, so you have it installed, but not loaded. So we'll load it and then load all of this data in as well. So do that first. In the workshop, we're going to work with dplyr and tidyr, which are sub packages in the tidyverse. And using those packages, we're going to select columns, filter the data. We'll use the pipe operator, this like %, which helps you sort of simplify the order of your operations. We'll use the mutate function, and then we'll do some summaries, group by, splitting data into groups. And then various other ways of like moving pivot wider, pivot longer to see the data in better ways. So getting a little more complex here. And just a note, we call this data wrangling, not data manipulation, because we are wrangling the data in a reproducible manner. So everything you do that you wrangle during this section, you'll document it and people will be able to see exactly what you've done. So we talked about the tidyverse. I'm going to skip this part. There's some explanation of dplyr and tidyr if you want to delve into that more. We're going to use the same data that we used in the data viz section. So this rodent data that has it'll have these same columns and rows. And we're also going to use the read_CSV. So let's also load this data in if you're following along. So yeah, again, it guessed the data type, and you can specify the data type differently if it ends up being different, but I think in this case it's correct. And we can look at the data here by using this glimpse function, which I don't think we used before. So this will show you each of the columns and then a few of the first values in each of those columns. And then it'll do view as well. I don't think we're going to do that because we did that in the data viz section of the workshop. This data is set as a tibble. This is just a review. And then Sally is going to come up here and show you how to use some of the most common dplyr functions, which are listed at the top here.
Okay, so we're gonna learn how to wrangle the data in a couple different ways. So we're gonna use select, filter, mutate, and then we're gonna work with date format data, wrangle that. And then we're also gonna learn how to summarize data within certain groups or groupings. So first, select, filter, mutate, or three functions from tidyverse that you'll probably use a lot. So select is selecting certain variables or columns. So we have our data set surveys. The select function, the first argument is the data set. See if it says that. Yep, so the first thing it's expecting is data. So if we just run that, we have not selected anything, so it gives us nothing back. But after we give it data, then we can just start listing columns that we want to pull out from that data set. So we'll do that. So we've said from the survey data set, pull out plot ID, species ID, and weight. And so those are the only columns that are returned. Everything else is not a part of this data set anymore, this output. You can also use it to deselect columns, to remove certain columns from your data. So maybe I did that other one. Okay. So we're going to start off with our select in our data set. And it says, try modifying this code to select all columns except for record ID and species ID. And so we have the solution to that right here. So survey data set is our data, and we're going to deselect record ID. So name that variable and then just put the minus sign in front of it. And then we're also going to minus species ID. If we run all of that, we have our entire data set except for record ID and species ID are not there anymore, no longer in this output. So we will use this a lot, and sometimes you just want to narrow in on a certain variable or get rid of some intermediate variable you've created. So you can clean up your data and focus in on certain variables. We also might want to filter the data. So select focuses on columns, filter focuses on selecting or deselecting rows. So again, filter function, the first argument it wants is the data set. So we give it surveys. And then the next thing we give it is a logical statement. We give it a variable name that we want to filter by. And then we have to evaluate for a certain value. So what this is saying is for the year variable, double equal sign is saying evaluate if it's equal to, and then the number 1999. And so if we run all of this together, it's filtering only the rows where the year is 1999. So it gives back the entire row, all of the columns, but only the ones that are 1999. So all of that meet that criteria. And so this part of the filter statement evaluates to true or false. So we can look at that quickly where surveys data set and select the year variable using our $sign, and then using the double equal sign equals 1999. If we were just to run this together on its own, for each row, for each value of year, it gives a true false. So a lot of these it's listing is false, false, false. These were all not 1999. Eventually gets to any trues, and it only keeps the trues. It keeps rows that were true. Filtering is about evaluating yes, no on some criteria. So some other ways you can filter, double equal sign is asking, is it equal to this? You can put a number or a character string if you're evaluating a character variable. You can use the opposite, not equal to. So to do that, we use exclamation point equal sign. Exclamation point is the opposite of whatever operation that is, so not equal to. We have just a comma you can use as something to evaluate, and that means and. You can also use ampersand to say and add certain statements together. Or you can use this vertical bar. So think if you hold down shift and backslash, that's the vertical bar character, and that means or. So if you put two different logical statements, one of them has to be true. You can filter for things that are less than, greater than. You can do less than or equal to, and you just put the less than and an equal sign together, or the same for greater than or equal to. So do a couple examples. So we're filtering surveys, and then year not equal to 1999. And you can see now it's including rows that have the year 1996, and there's a lot of rows, so we can't look at all of them in this viewer, but we can see so far there's no 1999s. There should not be any. And this is an example of putting two criteria together with a comma to say and. So filter surveys, the year equals 1999 and plot ID equals 2. So now both of those things have to be true for that row to be kept. So year 1999 here, and plot ID equals 2. And then the same works for ampersand. Is there a reason we changed that, Greta? Options? Okay. So this does the same thing. Okay, and then we can also do or. So same two criteria, but now only one of them has to be true. So either year has to be 1999 or plot ID equals 2, or it could be both, but at least one of them has to be true. And if none of them are true, then it's not included. So here, 1996, that's doesn't meet criteria, but plot ID does equal 2. So. Okay, and this is just less than or greater than, so we can see if or keep only rows where the weight is less than 8. So maybe you want to look at all the low values in a data set for weight, something like that. And it looks like weight, you have to hit the arrow on the right here to see all the variables if there's a lot of them, and weight is over here. So we've got weights of 7, 6, 7, 5. It keeps the original order of the data set. It just removes the rows that don't meet this criteria. So this doesn't mean like the minimum weights are 7 or 6 necessarily. It's just less than 8. Or hind foot length greater than 30. So it looks like it checks out. All these values for hind foot length are greater than 30. And in this preview window, it'll tell you the dimensions of this resulting data frame, or I guess this is a tibble, a special data frame. So it has 3,828 rows, 9 columns, so all the same columns, but it tells you, what did we start with? It tells you out of how many observations that we started with, that's how many meet this criteria. You can kind of see that. I think surveys, we started with like 11,000. So you can tell how many are kept just quickly looking at that. Okay, so yeah, filtering columns and filtering rows. Sound good, or that part's pretty straightforward? Okay. So now we're gonna go back to pipes, and we started using this with ggplots. So pipes, as a reminder, are that pipe operator, and if I can remember the shortcut, Control-Shift-M. Yes. Windows Control-Shift-M. I think Mac is Command-Shift-M. And so this again takes one object and passes the output into the next function. So a lot of times you're taking a data set that you start with something, and then you pipe it into a function to filter it down, and then you pipe that output into something to select a variable, and you keep passing that along to get this workflow where you have a polished data set. So that ends up being a lot smoother and easier to read and follow than the alternative would be using your intermediate objects or nesting functions. So just as an example of what those look like, you can do these, but they end up getting kind of messy, especially the more that you do. So we could start with surveys and filter to weight less than 6. So that's this function, and we'll save that as an intermediate object called surveys2. And now we're going to take surveys2 and select the species ID, sex, weight variables, and then save that as an object called surveys small. So, and then you could do another step that takes surveys small and create something new. So you keep creating new objects, and that works. And sometimes you want to save those intermediate steps, but it can really clutter up your workspace. You start naming things like 2, 3, 4, and you lose track of what you did where. Or another option is nesting functions. So we can start in the middle here. We've got our filter step, so weight less than 6. And then we want all the output of that to be the data that goes into our select function. So now that's the data within the select function, and we want to select these variables from that. And then you can imagine you have more and more steps that you're doing. So you don't have all the intermediate objects, but now you have this crazy chunk of code that is hard to keep track of what is where. So if it's just a couple of steps, maybe this is fine. You could also think like format it by entering down to like different lines to keep track of it, but then you start missing parentheses and commas. And so pipes are good. Pipes simplify things. Okay. And so I already I talked about pipes. So this is what piping one output into the next function would look like. We start with surveys, pipe into filter, and if you recall, it replaces whatever the first argument is. So filter, it expects the data set first. So we don't have to worry about giving it that. We just move on to whatever we provide the function next, which is this filter argument, the evaluating weight less than 6. So, and then we pipe whatever comes out of that into select to select species ID, sex, and weight. If we run all of that, this is what we get. And then we could continue to add more steps and refine this output. So we can also, this I think is the next step, but so when you run steps like using a pipe operator like this, it gives you this output, and this is the actual returned output is the data frame. So in this case, it's 7 rows by 3 columns, but you can save this as an object. So down here in the next code chunk, we're doing that, and then we're just putting the object name we want in the assignment operator and that first line where we started with surveys, and then everything that comes after that, it performs that and stores it back in this surveys small. And now it's stored in this object, and we can use it in other analysis or visualizations. And I think this is just talking about what I just described, how to use multiple steps with pipes. Okay, challenge. Okay, so let's try doing this. Using pipes, subset the survey data, and we want to include only animals that were collected on or after 2001. And we only want to keep the columns year, sex, and weight. So go ahead and try doing that and see if you can get all of those things accomplished using pipe operators. Okay, so what function do you think I should use after surveys? Filter, okay, I think that's a good idea. So it first asks us to keep animals. So animals are observations or rows collected on or after 2001. So we want to see the year be greater than or equal to 2001. Oh, 2001. Okay. And then, oh. Okay. And then we'll do our next step. So that leaves us with the select. We have practiced. So we want to keep only the columns year, sex, weight. So okay. So the year should be 2001 or later, and there's a lot of 2001s. So it looks like we filtered that, and then we only have the columns year, sex, and weight. Do you think it matters if we did select first in this case? Yes, no. We can try it. So if we selected columns first and then filtered, see. So we get the same output. So these don't really affect each other. You're just filtering columns and filtering rows. You can do them in either order here. But sometimes the order does matter. You need to do one thing before another. Something else you can add to your pipeline is the mutate function. And mutate creates new variables, or you can overwrite old variables to mutate them or change them. So a lot of times we'll want to take one measurement or column and do some kind of transformation. So here we have surveys, piping that to the mutate function, and you start with what is the new variable that you're creating. So we're going to name that weight kg. And then we're going to tell it how to create that variable or how to calculate that. And we're going to transform the weight into kilograms. So weight itself here is grams. So we can just do the mathematical operation, divide by 1,000. And it'll know for that variable, do that for every row, row-wise. And it'll create this new variable and add it on to the last column in our data set. So here we're just seeing what this output is, but you can also save this result to an object or even save it back to surveys. So you are then modifying the data set and adding that in. So it adds it to the end. So weight is still here, and now we also have weight in kilograms. So if we spell it wrong, surveys, we could run this and it would replace our surveys data set with this new surveys data set that has this new variable. You can also chain together multiple new variables in the same mutate function. So here we did the same thing. We're creating weight in kilograms and then just comma, and we'll hit enter to go down to a new row, and then you can just create more. And so anything that you create after, it already knows that this new thing has been created. So we can create weight in kilograms and then next tell it weight in pounds. And now it already knows that kilograms has been created, and you can use that. Even though it's all in the same function, it'll run one after another. So do that. And scroll over. So we have weight, kilograms, weight in pounds. So you can see the output in this little viewer. You can also use things like the head function, which this is a base R function. All of these that we're looking at right now are tidyverse dplyr functions. But you can include base R functions in your pipeline, and they'll mostly still work. Sometimes you have to figure out exactly the format to do it. But so, for example, we're taking surveys, creating a new variable, and we just want to see the first few rows of the data. We can use the head function, and this base R function still works in the pipeline. And then we can just see from this little bit of data that there's these missing values, NAs, for a few different variables. So this is something we might want to filter, get rid of missing values. So we can filter on, I think we looked at NA omit before. If we did surveys and then pipe into the NA omit function, it would get rid of any row that has any missing value. But we can also just filter if we want to get rid of certain missing values for a certain variable. So going back to filter, surveys, filter, and then what we're evaluating is the weight variable. So we're using the function is.na around the weight variable. So this will go through and determine, is the value in this row for the weight column, is it NA, true or false? And filter, remember, keeps anything that's true. So if we filtered by is.na, it would only keep missing values. We only want to keep non-missing values, so we can put the exclamation point in front of this function to get the opposite. So if we just run this part, we can see weight now does not have missing values anymore. Those rows were removed, but rows that had missing values in other variables, those are still left. So do that, and then we can use weight to convert to kilograms, and then view the first few rows, do that whole pipeline. So these are pretty common steps that you might use creating a workflow in your own data analysis. It's filtering out missing values, and then create a variable, and then maybe view the output. So, okay. All right. So now we're going to do a challenge and put together multiple steps. And a hint is the order does matter in this workflow. So we're going to start with surveys. And we're going to use a bunch of pipe operators for commands, and we're going to save the total output as a new object called surveys underscore hindfoot underscore CM. And then here's all the steps that we want to do to it. We want to keep only the species ID column and a new column. So we want to create a new column called hindfoot underscore CM. And we want to create that from hindfoot length converted to centimeters. They're currently in millimeters. And then we only want to keep non-missing values. So get rid of NAs. And we also want to filter out rows based on not missing, and we want only rows that are less than 3 centimeters. And then after that, just use head to print out the first few rows. So try doing all those steps and figure out if there's a specific order you should use, and see if you can get that all together using pipe operators. Hindfoot length is in millimeters, and we want to convert to centimeters. So I think it's divide by 10. Change by 1 order of magnitude. Okay, have some ideas, getting somewhere, kind of. Okay, so let's kind of start figuring this out. I think the first thing, if we just went in order and did surveys and then pipe into, we want to keep only species ID and in the new column. Well, that would be select and keep species ID. And hindfoot length, oh, hindfoot CM. So the problem already is we can select species ID, but we didn't even create this variable yet, so we can't even do that first. And says can't select hindfoot CM doesn't exist. So that cannot be our first step. So let's maybe create that variable first. So create a variable with mutate. And we want that to be called hindfoot length. And that is equal to, hindfoot CM is equal to hindfoot length. And we're going to divide that by 10. So this part of it, okay, we've got that and that works. So we have our new variable at the end here. Looks good. And we want to only retain values that are not NA and are less than 3. So let's filter next. So not NA, so exclamation point is .NA. We want it to be non-missing on only the hindfoot CM column. And then, and they should also be less than 3 centimeters. So here's our centimeters, and that should be less than 3. So we can do both of those at once. I think in this case, you could have these as 2 different filter steps too. First, get rid of NAs, and then get rid of anything over 3. And then we want to save all of this as a new data frame called surveys hindfoot CM. So let's see what this gives us. Okay, so we created a new variable, filtered, and then kept only these 2 columns. And we want to save this output data frame into an object called surveys hindfoot CM. We can run all of this to store it. And then with that, we want to just look at the first few rows. So we can do a new pipe and put that into the head function, and that gives us the first 6 rows. If you include head and this pipe operator in your workflow that's being saved into your new data frame, your new data frame will only include 6 rows then. So just be careful of what you're including when you save an object. Maybe that's what you want. Okay. We'll do dates next, but any questions? Pretty logical, just working through do this, then this, then this. It's the pipe operator. Yeah.
So the idea of intermediate object,
Mhm.
is it really, should we only save, or not even save, but store intermediate objects, like intend to use them earlier or later or save them to like something like that? Is there much use for it outside of that?
I would say no. Sometimes it's nice to have intermediate objects if you're kind of troubleshooting things and you just want to have those objects to look back at to figure out steps. But in the end, if they just sit in your environment, you're never going to use them. It's sort of just clutter. So if you can avoid making some of them, it'll help you stay organized. And especially like if you're sharing like this document with collaborators, and then they wonder what are all these other things that aren't important. So yeah. Yep. Okay. Okay, so yeah, these three functions I use constantly. So and pipe operators I use all the time. So it's very good to know. And there's a lot of other things you can include in your sort of pipeline too and get real fancy. We'll do some more of that, but after this. But first, we're gonna jump into dates. So a type of data value that we haven't talked about yet, you can have date formats. So like text strings or numeric variables, you can have date variables. They're very frustrating though, because there's several different formats of date time data. And you have to figure out which one you're working with. The format, is it giving you years first? Things with time, there's time zones, leap days, holidays, daylight savings. So it can be tricky and annoying. So we're going to use the lubridate package, which is a part of tidyverse. So it includes certain functions that like listed here. So we have year, month, date, day, month, year. And so it keeps that kind of simple, and you can create the format of date that you want pretty easily. So we will first load the lubridate package if it's not already loaded when you load tidyverse. So that's the library lubridate. Just make sure that's loaded. Run that. And then just by using the functions today or now, no arguments or anything, it can just tell you what today is and what now is. So year 2025, August 8th, or now includes the time. So hour 15 minutes, 47 seconds, 55, and the time zone, Mountain Daylight Time. So these are useful to automatically fill in dates, or sometimes if I'm trying to figure out how long a function or a chunk is taking to run, you can do like now before and then now after, include it twice, and it'll automatically output that so you can see like the real time it took to run something. And we're just going to create a little data set using dates that we can work with. So that's what these lines of code do here, and you can just run that. And the function that's using is this YMD to create a text string with year, month, and day. So those are all variables in the survey data set, so we can create a new variable using all three of those together. And then from that, we have the date, and we can create day of week using wday. So that function takes a date and it automatically knows what day of the week that is. So what does this look like? Okay, first few rows, let's see. Date, we can see that it's in the year, month, day format. And it gives us a day a week. So January 27th, 1996 was a Saturday. So that's useful. I think when we created this, let's see if we can. So when we ran this to create these date variables, if you scroll down to the output, it does give you a warning. It doesn't give you an error and say, this doesn't work, but it says, okay, I'm going to do this, but there is a problem. So the warning is when it created date from year, month, day, there was a warning, 125 entries failed to parse. So not very descriptive. There's some kind of problem. We don't know what it is. These are probably ended up as NA values. So let's see if we can figure out what happened there and try and see if we need to fix it in some way. So if we do summary, we have our data set and we're piping that into select, and we are only going to look at day of the week. And then we're going to use summary, so the base R function, and run that. So it's giving us a summary of the day a week function. And there's 4,000-ish Sundays, 4,000-ish Saturdays, Wednesdays, Mondays, Thursdays, other, and then 125 NAs. So those are the ones that I think came from that warning. I think other is just there's more options and it's just lumping them all together, like Friday and 1, 2, 3. What day? Tuesday. Yes. Thank you. So it's just not specifying, but there's other levels. So, okay, let's try and look at what are these NAs that were created. Let's look at the other data that's associated with those. So the data, and now let's filter and let's keep only the NA values for date. I think the code up here, we want that to be equal to true, but I think if you get rid of this, is NA will evaluate to true or false. So, and it'll keep the trues. So we're going to this first filters. So we want only NAs to see what the problem is. So date is NA, day of the week is NA. Let's maybe look at month and day for those entries. Okay, month is 4, day is 31. And we can kind of summarize that by creating a table of the different combinations of values for month and day. So that's the table function that is also base R, I think. So let's run this whole thing then. Okay, so the output here is saying the different NA values have a month of 4 or 9, and day is 31. And there's 70 entries that are month 4, day 31, and 55 that are month 9, 31. Does anyone see the problem? Yeah, so what's happening here, it's saying, okay, the data recorded in this data set we imported, it's saying the month is April 31st, or the date is April 31st and September 31st, and those aren't real dates that exist. And so when we use the date function, it knows that those aren't real days, so it gives us NA. It doesn't know what to do with that information, doesn't make sense. And then since we don't have that date, it also can't convert that into a day of the week. So something like this, you have to figure out what you want to do with that. Is it a data entry error? What else is it a typo that happened to all of these? Can you correct it, or do you just have to throw away these observations because you can't be sure? Maybe we don't care about the date, so this is a problem, but we're not going to be using this in the future. We're just going to use like weight and hind foot length or something. So so decisions after you figure out what's going on, then what do you do about it? So that was challenge 3, was figuring that out. And then we can also go in reverse. So once we have like a date, we can use functions like year, month, hour, minute, and that will just take that part of the date and create a variable that's only year or only month, and it'll still be in the date format, but it knows which parts to pull out based on these functions that you give it. And then there's a link for the Lubridate website has a nice documentation and examples of how to use it. So if you visit this link, figure out what else you can do with it. There's also a cheat sheet we have. So a nice little guide on different functions that you can use with Lubridate. Okay, and then another challenge here we're gonna do is we're gonna look at the day of the week variable. So we created that. And then we're gonna figure out what type of variable it is, and we're gonna see that it's ordered. So that's a specific type of factor variable. So let's do surveys. Oops. What was the data set called? Surveys W days. Okay. So this is our data set. And And then we can just use our quickly day of week, use the $ operator just to look at this column really quickly and do class function. And it tells us the class is it's ordered and it's a factor. So ordered means it has specific levels, but the order of those levels matters. Just like Monday should always be before Tuesday, and then Wednesday, etc. So what are the names of the days of the week that were taken from these dates? So we used this before to look at factors, and we can just plug this into the levels function. Okay, and so this is what the levels are for day a week: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and it's in that order. But it's just the abbreviation, it's not the entire word. So maybe we want to relabel that to include the entire word. So maybe if we're plotting it, the entire word shows up on our plot and it's more clear for people that are looking at the plot. So in order to change each of these, we're going to use something called case when. And case when kind of does a series of if-then statements to create new levels. So if we look at how it's used here, we have our data set, surveys with days. We're piping that into something, but we're saving it as a new data set when we do all of this. New data set called surveys days full. So data frame, and then we're gonna then mutate it and create day of week, which we already have. So we're writing over the top of that variable to create the new version of that variable. And then to create that, we're gonna use case when, and it's gonna be the variable you want to evaluate, and then some evaluation case. So like before, when we were filtering, like double equal sign, when we say when the variable day a week equals mon, M-O-N, we then wanted to take on the value of Monday, this entire character string, not just the 3 letters. So it's saying if this first part is true, if day a week equals mon, then we want it to turn into the character string Monday. And then it goes on to whatever next if-then kind of statement. So we can keep doing this and say when it equals 2, we want it to be Tuesday. When it's wed, we want Wednesday, so on, go through all the days. And that's all within this case when function. And then down here, we're closing up the mutate function. So completing that whole variable mutate, what's that? And then glimpse, we're going to look at that new variable. So glimpse is the equivalent of str. So character variable, 11,000 plus values. And here's the first few values, Saturday, Saturday, Saturday. Think we get to this in a challenge, the challenge 5, but pay attention how this might be different than what we started with. So going back to case when, we can also set it up however we want. So maybe instead of defining each day of the week and changing it, let's create a new variable called weekday. So surveys with days, and mutate to create the weekday variable case when. So when the day of the week equals Saturday, let's give it a value of 0. When it's Sunday, give it a value of 0. If it's Friday, let's turn it into an NA. And anything that's not Saturday, Sunday, or Friday gets a value of 1. So what this ends up doing is Saturday and Sunday are zeros. Days of the week are 1, except for Friday is erased, missing values. So if we run this, This is just a summary of what our new weekday variable looks like. So there's now 8,000 some zeros, 2,000 some ones, and then 300 some missing values. So that's what we got from this case one. So you don't have to think of every scenario of data if you don't need to or want to. So this true tilde 1 is just everything else gets a 1, no matter what value it started with. So you know, you don't have to think of all the rest of them. Okay, so if we grab up here, we were looking at this surveys days full. So this is, we renamed all the days of the week. Let's copy that down here. So here's the variable. What order did it put the days of the week in? So we just renamed it. Let's try doing levels again to see if the levels are still match up. If we run that, well, now it says no. So what happened there? When we did glimpse, or we can use str and look at this. So now if you notice, it is now a character variable. So it undid that factoring. It doesn't have levels anymore. So it's just a bunch of character strings that we named according to different cases. So they're not in any order. And so we should fix that. And it's ordered, so we know that, you know, Monday and then Tuesday and then Wednesday. So in order to do that, another package for categorical factor variables that's really useful is for cats right here. Also in the tidyverse. So it's for categorical variables for cats. And then within that package, there's a function called factor relevel, and that makes it really easy to add those levels back in and put them in the order that we want. So take the data set, mutate, and we want to change that variable, not create a new one, just change that one. And then the factor relevel function. So within the function, you're giving it the variable to change to create a factor variable. And then you just list the levels in the order that you want them, and these should match up with the exact text strings that you want to be those levels. We can run that and check our data again with glimpse. And now we see it's factor. It has 7 levels, and it starts with Monday, Tuesday. We can look at the rest. Levels, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. So that looks good. We have the full names. They're in the order we want. It knows they're categorical. Oh, and I did challenge 6. Verify that they're in the order you specified. You can just use levels to look at all those levels. Okay. So that's dates and dealing with categories. Like that. Any questions? Yeah. Mm-hmm.
We originally created a week
Mm-hmm.
variable. Could we sort of, maybe there's teaching, but could we have just made them not abbreviated initially? Or did we have to make them the abbreviation and then change them?
That's a good question. I don't know, but maybe let's look quickly. So, oops. So we created the day of the week, and it was automatic using that wday function. So maybe if we look at wday, it'll tell us if there's any options. I'm just gonna open that in help viewer for more details. I have a feeling you can give it a custom argument to tell it what format you want. A lot of times it'll give you options like that. Yeah, kind of in the same way that the date function, you can tell it you want year, 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 the 4-digit year, 2-digit month, stuff like that. A lot of times there's arguments in there that you can say, I actually just want like this many digits or the full name or an abbreviated name.
So it's pretty custom.
See if we can find this. Okay, so a lot of these are grouped together in the same help thing. Okay. Ah, there we go. Okay, so W day. And it looks like we give it the data, label, we can look up what that is. By default, it's false. Abbreviation, by default, it's true. I bet if you turn this into false, it'll give you the whole name.
So what it shows there, that's what it's set to.
Yep, exactly. Yes. So like X here doesn't have a default. You need to give it data. But if you don't tell it anything, it's going to say label equals false, abbreviation equals true. So there's a lot of like default things. Yeah. Good questions. Yeah, and it'll give you details. Label is true or false, logical. Okay, true will display the day of the week as an ordered factor of character strings. False will display it as the number of the day of the week. So label is, if you have that as true, it'll give you, this is the first day, second day, third day of the week till 7. So yeah, you can always look up a function to see if it has options like that, if you're wondering. Okay. All right. Did we get everything off of this chunk? This all makes sense? We're closing in on all the last stuff. We are experts. Okay, so the next part is basically how do we create summaries of certain variables? Maybe you want to group together things that are similar on a certain dimension and then create a summary like a mean or a minimum value. We can do that in our workflow pipeline with the pipe function or the pipe operator. And then the function we're going to use is summarize, group by, and summarize. Those two kind of go together. So, for example, start with here we're using surveys edited data set. It's one of our versions of the data. And then we're going to group by a categorical variable. So easy one is sex. We're going to group those together. And if you just run this part, here's the data frame. It looks the same as always. But you can see at the top of the viewer here, it says groups equals or colon sex and then 3. So it's saying that there was 3 different sex values and it's grouping those 3 different types together. And now anything you do in your next steps in your pipeline, it's going to treat all of those together. It's kind of a group-wise operation. So we've grouped those. So let's summarize by those groups. Summarize, you can create any calculation and it'll just return one row of summary values. So here we have all the data and it's grouped by sex. Summarize, we're going to create, well, we want to calculate the mean weight for each sex. So we have our mean function, we have our na.rm to deal with missing values, and then you can just tell it this operation. And then what we have here is we're just going to give it a nicer name. So we're going to call it mean weight. And if you run that. So now here's our summary. There's a line for each group. So female, the mean is 33.1. Male, the mean weight is 33.3. And then it's also picking up that there's a group called NA. So it's counting missing values as its own group. And then it's trying to calculate the mean weight of those. But it doesn't work. So it gives us this output nan. This is not a number. So it's probably, sometimes you get this like if you divide by 0. We may or may not be interested in the mean weight for missing sex values. So we can just add a step in our pipeline to filter. We want exclamation point not is NA sex. So let's not include anything that has a missing sex variable. And so now before it gets grouped, it removes that missing values that turn into that third group. So you can add that in too before you group. Okay. So you can also group by multiple variables. So we're grouping by sex, one variable. We can create groups of multiple things. So let's try grouping by sex and species ID. And if we just run the group by portion, we can look at groups is sex and species ID. And the combinations of those two, there's 25 unique combinations. And if we summarize the mean weight of those groups, so we have female for the DM species, female for the DO species. It goes through all the females for each species, and then it goes through all the males for each species. So it lists all those combinations, and it calculates the mean weight for that intersection of these two variables. So do that to get more specific breakdown of mean weights. And this is just talking about NANs. We can see that in here too, this actually gives you more information because we had more specific groups. So missing sex, but it was in the DM species. So you can maybe narrow it down. Okay. Oh, and I just went through this, how to filter out the NAs. So we don't include that. It doesn't include that NA, NAN row. This is going over the print. Print is a base R function. And this is useful, like when we're working in our studio in a markdown file like this, it always gives us our output data frame in this little viewer that has 10 rows, and you can scroll through all of those. But if we were just using this in the console, it would not give us all of those rows. So we have to tell it how many rows we want. And so if we enter in the console down here, it's giving us output in the console, and there's 15 rows. So you can use print to do that. It doesn't usually make a huge difference in your code chunks in a markdown file. Okay. So you can group by multiple variables, have to be categorical. I think you can do numeric, but it'll just treat each number as a different category. You can also create multiple outputs from summarize, and they don't have to be on the same output variable. So we're going to group by sex and species ID again, and we're going to create mean weight, but we're also going to create minimum weight. And this could also be like minimum hindfoot length. It doesn't have to be weight. So you can mix and match the summary that you're making and the variable that you're calculating that on. So here we get, we've got all of our groups over here. So now we have our mean weight, and we also have the minimum weight. And those are all listed. And sometimes we want to get an idea of maybe the smallest or largest in here. And so we want to sort by one of these columns, arrange from highest to lowest or lowest to highest. So here we have our kind of usual code to create the minimum weight, mean weight. And then we just add on the arrange function and tell it which column we want to sort on. And by default, it goes from lowest to highest. So here's that output. And now mean weight, minimum weight. The minimum weight of all of these groups is 4. And you can see that that's for males from the PP species. And then you can see the associated mean weight for that category. So 17. The next minimum weight is 5. And you can see that the mean weight is a lot smaller. So you can start comparing things more methodically. We can also sort in descending order. So same thing as above, but now we add this DESC function around the variable within the arrange function. And this just modifies it to go in the opposite direction. So now we've got the minimum weight and we have the largest value first. So females from the NL species. Okay. Are we okay on time or should I speed it up? Okay. 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 So this is just kind of practicing what we just talked about. And then the last little part about grouping by to create these summaries, there's a special function that kind of does this all in one. It's the count function. So counting is creating the specific summary of number of observations. So we have our data set. And instead of saying group by and then summarize, we can just put the variable we're interested in the count function. And you'll see that this looks familiar, this type of output. So it appears to have automatically grouped by this variable, grouped by sex. So our 3 options here. And then the summarize output is always n, so the number of observations. So this just counts the number in each category. So we can see that. So next code chunk, you can do the exact same thing using group by and summarize. And this is group by sex, summarize. We're going to call it count. And then the n parentheses function, that just counts the number and it doesn't have any other arguments or parameters. So if we run this, it's the exact same output, but more lines of code, more to remember. You can just use count and it accomplishes that. And then maybe if we want to arrange the count by smallest to largest or largest to smallest, count has its own argument. Instead of using the arrange function, you can use arrange, add that in after count on another line. But it also has a parameter called sort, and you can add that equals to true, and it'll automatically arrange that in order. So there's the most observations are male. Might have a descending argument too. Maybe not. So you could play around with how to get it in reverse order. Maybe use a range. Okay. Okay, so this is just saying that you can use count in the same way as group by, where you can list multiple variables to group by and then count. So we're going to list sex and species ID. And now it'll count the combination of the different options for sex and species. So you can also add multiple variables the same way you use group by. And so you can also arrange by multiple variables. So let's say we have that output. Let's first arrange from an alphanumeric order the species and then look at the count. So we want, starting with A, B, C, D to all the way to Z, list the species. And then we want within a species, we want the count, but we want that in reverse order. So largest count within a species first. So it's first sorting on species. So everything from this species first, and then everything from the next species in alphabetical order. So within this species, this is the first group that it sorted on, and then now it's doing descending n. So within that, the largest n first, and then all the way to the smallest. Okay. So how can we use this to quickly find information about our data set? We've got our data and we want to know, okay, we know that there's 72 observations from the NL species. What if we want to know how many animals were caught in each plot that was surveyed? So try stringing together group by arguments, summarize, see if you can come up with how to answer this question. How many animals in each plot? Okay, so hopefully you're thinking about grouping by plot ID. And we want to know how many. So maybe the summary measure we want is the count. So we could just shortcut by using the count function and counting by plot ID. And there's a typo in the comment that says plot type. It's plot ID, which is the plot type or specific plot. So just surveys, data set, type into count, and we want to count by plot ID. We get this summary. So plot ID 1, how many were in there? Plot ID 2, how many were in there? So we get this summary of all 24 different plots. And then maybe you want to know, was there a plot that, which plot had the smallest number of observations? And this is where we could just add on arrange. And then arrange by n, so smallest to largest count. And then you quickly know that plot ID only had 55 compared to some of the other ones. So you can answer questions quickly about your data using summary measures like that. Okay. Okay, and then Greta is going to keep pushing on.
Normally we would take a quick little break here, but because we're almost at the end of the day, we're just going to briefly touch on some important things like joining and exporting data and closing out our knitting, closing out your project and so on. So there's going to be some of this, the next section that I'm going to skip or cover really quickly. You do have the packet that you can go through again, and we have other videos on YouTube where we cover the full session in more detail. So the idea here is that we might have repeated information that we have over and over again, and we don't want to have to, if we're out in the field, we want to just record the measurements on the animals that we observe. We don't necessarily need to record that plot ID 1 was a particular type of enclosure. And maybe we don't need, there's other information. We don't need to record that DL means a particular species. It's just a shorthand that we use. And when we get back into the lab, then we'll bring in all the information from extra data sets, and we're going to join it together so that we have a complete data set that has all the information in it. So we've got two other data sets. One is plots that has all the details about the plots that we're going to bring in. So plots just has plot ID in it and plot type. So plot ID, if it has a 1, then it's this spec tab exclosure. 2 is a control type plot, and so on. And it's just a simple lookup file that has just those two pieces of information in it. In our species file, has the species ID, it has the genus, the species, and the taxa in it. So it has all that detail that would just be repeated information that we don't need to record every single time. But when we want to go and visualize this and summarize it for reports, then we need all of this information together. And how they connect together is through keys. And so the key for the plots data that's going to link to the other files is going to be that plot ID, because it's the same thing that there's one row for each ID, and we'll use that to link together. And then the key for the species data is going to be the species ID, so that we remember what is our linking variable. We like to put the ID in part of the variable name. The key for the surveys data table is actually the record ID, because for each row, we're going, for each observation, it's going to have one record. And so the key, the lookup, is unique for every row. There's going to be multiple rows with the same species, multiple rows with the same plot, and so those are not the key. The record ID is the key. So that in a particular table, the primary key identifies an observation in its own table, and then a foreign key identifies an observation in another table. So in this surveys data table, species ID and plot ID would be foreign keys. Okay. These figures aren't showing up here, but they're in the documents. So let's just really quick here, relations, and lost my connection to the folder. There it is, OneDrive. Desktop. All right, so I want to open up the relations image. So let me make this bigger. In the surveys data set, plot ID is the primary key in the plots file, and it's a foreign key in the surveys data set. In the species file, species ID is the primary key, and it's a foreign key in the surveys data set. So they link together, that have repeated information. When we join them together, we're going to use something that's called a mutating join. And the simplest join is an inner join, which joins a pair of observations whenever their keys are equal. And let's inner join, open that image up. So an inner join, it has to have a one, it has to have a one in the left-hand side, a one in the right side. If they're in both files, they come together and join together. So 1 and 2 are in both files, so they're in the final result. 3 is only in the left, 4 is only in the right, so those are dropped from the final output. An outer join, let's see, we want joins. So outer joins can be different types. So a left join keeps all observations from the left, whether or not they match on the right. And if it's on the right but not in the left, then it's dropped. A right join is the opposite. So it keeps everything from the right-hand side and only keeps matching things from the left-hand side. Everything else is dropped. Any columns that don't match are filled with missing. And a full join keeps everything from the left and everything from the right and fills in missings whenever they don't match. There's one other one called an anti-join that I use to find observations that, to identify observations that don't match, just so that I can investigate them further. But we're not going to do that here. So we're going to primarily use left join. So we're going to start with a data set, and that's going to be our left-hand side, and then we're going to join on the right our plot ID and our species ID, And we're going to, since we know that the names match identically in both files, we just need to use this argument by equals and then the name of the key that we're using to join. We're going to put this into combined and then we're going to glimpse it. And so now we have through all the work that we've done through day of week from before, now we know the actual plot type name, the genus, the species, and the taxa from the species file. So we have complete data set now. That's why we called it complete. If the key being used have different names, this is a little bit weird. You have to use by equals, C for combine or concatenate. A is the foreign key from the left-hand side, and B is the primary key from the right-hand side. So you have to link them together with equal signs. If you were linking on more than one column, then you would put a comma in here and have, again, left-hand name equals right-hand name so that they come together. Any questions about that? All right, reshaping data. So generally we like to have one row per observation. Each variable has its own column and each value has to have its own cell. And then each type of observational unit would form a table. So, and now my images are showing up. So variables are columns, observations are rows, and values are in each cell. So we want to examine the fourth rule. Each observational unit forms a table. And so in surveys edited, the rows of surveys edited contains values of variables associated with each record, which is the unit. And the values are weight or sex of each animal. But what if we wanted to compare the different mean weights of each genus between plots? So we're going to just use plot ID. I'm not worrying about plot type for right now. And so we would need to create a new table where each row was the variables associated with each plot. So genus would become the names of the column variables and the cells would contain the values of mean weight observed on each plot. So to do this, we need a reshape, and we're going to reshape using pivot longer and pivot wider. The other reason why I use pivot longer and pivot wider is if I have 100 columns and I want to perform the same operation on all 100 columns and they're the same type, then I'm going to pivot longer and make one really long data set that has all that data in one column. Do the operation once, pivot it back longer, and it's a lot quicker than writing a for loop to go through each column one at a time. So pivot wider takes three principal arguments: the data, the columns whose values will become new column names, and the column whose values will become the fill of the new columns or what's going to go into the cells. So we have a little image here. Let me make this one bigger. This one is pivot wider. So here we have the plot IDs, 1 through 3. This is just a subset, and the names are going to come from the genus column. And we already have calculated the mean weight for each plot ID. And we want, for each plot ID, we want the genus in columns. And so we're going to we're going to take all the genus and turn them into column names. And we're going to take all the mean weight values and make them in the cells. And so that's going to happen by taking our data frame where we have this information summarized. The names from are going to come from the genus column, and the values from are going to come from this mean weight column. So here we're summarizing to get that information. So from our combined data set, we're going to remove all rows where the weight is missing. We're going to group by plot ID and genus. To get that summary table, we're going to summarize the mean weight, and we don't have to worry about missings anymore. Let's glimpse that to make sure it sort of looks like that graphic. It's not going to look exactly because we subsetted the data out. We have our genus, and we have plot IDs are repeated. That's okay, and mean weights for all of those. And let's look at the head of that. And it's just a different, better way of looking at that. So this is our long version. And so now we want to pivot wider on that. So surveys GW, pivot wider, names from that genus column, values from that mean weight column, and let's see what we get. Does it look like the graphic? It does. So we have unique plot IDs in rows, and then all of the genus, and then the mean weight is filled through. So it's kind of the opposite of what I said that I normally do, but this is, you know, one good way that you could summarize your data and maybe use this for visualization. So we're going to skip the challenge for right now. But let's go the other way. Let's pivot longer. And so let's say that we had our data stored like this and we want to go backwards. So pivot longer takes the data and the columns that we want to pivot into a single column. We need to give it a name of the new column that's going to have the names of the old columns and the name of the new column just for the column that contains the values, the data values. So let's look at our pivot longer graphic. So it's just going back in the opposite direction. So names 2 is going to take all the column names and it's going to say what should the new column be named. And the values 2 is taking all the values from the cells. What should that column name be? Because these are column names that it doesn't know anything about, we have to provide those in quotes. They're not objects themselves. And we have to tell it which columns are we actually grabbing data from. We don't want to use plot ID to go into this names to, because this plot ID is our unique identifier for our rows. You could have other information here that was that you wanted to stay consistent, that you didn't want to pivot longer and you wanted to have, you know, just like the meta information about each plot ID that shouldn't be captured with all the genus information. So we're excluding plot ID, so there's a minus sign in front of plot ID. Our names are going to genus, values to a mean weight, and so those are going to be the new names of the columns, and let's glimpse that. And so here it should look pretty similar, only now we only have that to what we started with, but now we only have these 3 particular columns. And there are some missing values. When we pivoted wider, we made it a rectangle. We made it a box. So whenever there was a plot ID that didn't observe a particular species, it filled that in with missing. So now we should have more rows than we originally started with in the surveys GW, because we filled in anything that wasn't observed with missing. But now we have in the long form all possible columns. And you could go back again. You could, oh, this is just showing that you could select just a subset of columns that you wanted to pivot longer. So if we only wanted this genus to that genus, I can pronounce Sigmadon, but I don't know how to pronounce that one, so I'm not going to. And then now we only have 6 rows because we just are looking at a subset of columns. And we're also just looking at the head. Okay. And so we can go back and forth, pivoting longer, pivoting wider. Again, if I wanted to say, taking all of these columns, if I had my wide data set and I wanted to filter all of these plot IDs such that all of the weights were less than 10, I would pivot it longer so that I could just do that filtering on one column and then I could pivot it back wider if I needed to. Or if I wanted to take all of these columns and divide them by 100, if I pivot it longer, then it's just one mutate on one variable and then I could pivot it wider again. So instead of having to go through each column and divide them one at a time by 100. Any questions about that? Similarly, if we wanted to know the overall, the grand mean weight, and we could just do the overall grand mean weight without summarizing based on species or genus to begin with. But if we started out with a wide data set, if we pivot it longer, then we could get an overall summary of all of the weights as well. Okay. So I'm going to skip the challenges. Now, exporting data. So before I go through this last parts, any questions? I know I went over joining data and pivoting wider and pivoting longer really quickly. The pivoting wider and pivoting longer, the biggest thing is make sure that you put quotes around your names to variable names because they don't exist. Other than that, they're pretty straightforward. Yes.
I just have a question. When you're, I guess when you're working with a data set, is there a certain, like, does it just depend on what you're trying to do to it, or is there a certain format that it's easiest to remember?
Whatever your observational unit is, you want that to be your rows. So for instance, if you have one subject and you so like these plot IDs, right? If we went to this plot many times over many years, we don't really want plot ID to be our row. We want each time we went to the plot to be our row. And as long as you can get it to that way, oftentimes people will record data where, like in a logbook format where you have a plot ID and then each column is a particular time that you go out. That's not very useful for actually doing data analysis. So then you'd want to take that and make it longer so that each time you went to a particular location would be a row. And that's basically the goal. As soon as you can get to what you consider your observational unit as a row, then you can work from that. Does that answer your question?
Yeah.
Okay. All right. So exporting the data. We used read_CSV to read in CSV files. So we're going to use write_CSV to write out data files. And we already started our workshop with having a data folder. And we do think that this is best practice, is to have a data folder that you read that contains the data that you're going to read in, and you can write out your data to that folder. I'm including this line of code here just because if you're doing this in a script format, you might not know if the data folder exists. So we can ask, or we can use this dir.exists function to say, does this function exist in this file? And it doesn't, and I need to make sure my session is source files location. Now, if I do that, session files pane location. Oh, okay. So it's saying if it doesn't exist, but it does exist, so it should be true. So dir exists is true. All right. So the not says if it doesn't exist, then use dir create the data file. But it already exists, so I'm not going, this won't do anything. So we're going to just clean this up a little bit. So we're going to take the surveys, edit it. We're going to remove any rows where the weight is missing, remove any rows where the hindfoot length is missing, and remove any that are missing the sex because they just went across or went through the plot so fast that we can't even record anything. We'll glimpse this. We have to verify it has everything in there that we want. It doesn't have anything that we joined in because that's just redundant information. And now let's see, let's maybe summarize a little bit. species counts. We're going to just keep the species that have more than 50 observations. Maybe we don't really care about the tails, the rarely observed observations. We're going to take the surveys complete, filters to have the species ID that only the ones that have at least 50 observations. So new function that we haven't talked about, percent symbol in, percent symbol means that it is contained in. So species ID is contained in the species counts data frame species ID. So it's one of the species that's observed at least 50 times. That's our subset. Let's glimpse that. We did get some reduction down to 11,266 rows. And now we're ready to save it out. Write underscore CSV. The first argument is what the object that we want to save out. So write underscore complete underscore subset. We're going to give it a file name. And we're not in the data folder. So we want to go into the data folder / surveys underscore complete underscore subset. If I'm going to be modifying this a lot and making changes until I get to a stopping point, I will put the date at the end of it, just so that I know that it was the version that I created on a certain day. And we'll write that out. Now, if we go into our data folder, we should see it in there. Any questions about that? Right. If we've resolved all the issues, we should be able to knit this now. And if you knit to Word, even if you don't have Microsoft Office on your computer, it'll still create a docx file that you can then open with Google Docs, but it won't automatically open. You can also knit to PDF, but that requires making sure that you have TinyTech or MikTeX or some sort of compiler on your computer. And so if you're going to be doing a lot of research where you're going to be using R, we recommend getting that set up. But everybody should be able to knit to HTML. And it's also the fastest compiler. So that when you knit it, it starts from the very beginning, goes all the way to the end, reruns everything. It doesn't use anything that's in your environment. So if you played around with things and then abandoned it in the console, it's not going to use that. And because we viewed a file, it popped up this little window. So if we have any help things that are help windows or help calls, it will pop up a window for the help file as well. And let's see. We get a little bit of a progress. This is kind of a massive file, so this might take a while to do. And then while this is running, if there are any code problems, it'll bail out and say that there's a code problem, and you can tell you approximately where to go back and fix it. And when you knit, it also automatically saves before you before it starts knitting it. So you're getting two things in one. You're getting a publishable, or you're getting a viewable report, viewable output, and it's also saving your file for you, so you don't have to remember to do that later. And then you could just, after it was done with this, it will create an HTML file that's going to stay in the same location that your RMD file was, so you don't have to worry about it disappearing. You could just close RStudio and open up the HTML file. HTML files do require that you send, if you were to share it with somebody, you'd have to share all of the little image files as well. So it's not quite a complete document. If you were to close this, again, make sure that you don't save your environment or your R data file. While this is working, oh, now it's going to go a little bit faster. Any questions? Yes.
So if my goal is to, let's say I'm just doing the data wrangling piece and it's just to get a CSV or some type of tidy data set out of it, Would you still work in an R Markdown file, or do you think an R script is fine?
I generally work in RMD files because I like to document my thought process while I'm going through and doing it. You can also, and I did end up having a little bit of a, where it's not quite complete, so this isn't going to compile. You can go into visual mode as well while you're working, and it's gonna take a little bit to do. The visual mode will look more like a final report as well, and tables and images will be included in there. And so it would be, the visual mode is like more like working, like if you're in Word or Google Docs. But I like, you can document your process by putting in comments with hashtags and document that, but then you get into problems with code going too long. But when you are in an RMD file, then you can just write and it'll wrap. And you can, have all of your steps, and it's a lot easier for people to follow.
So if you're sharing, yeah, it's just like a easier way, so you don't need to comment everything out.
Exactly. Yeah.
And
Yeah.
then-
So like I'm going to do these filtering steps in this order. You can do itemized lists. And itemized lists, you can just use the number 1 over and over again. And then when it compiles, it'll turn it into 1, 2, 3, 4. Or you can put in 1, 2, 3, 4. And that'll work as well. So it's, are you doing the RMD file to get a nice PDF out of it, or are you doing it for your documentation purposes? You can also do both.
Okay.
So, other questions? We didn't talk about projects. This is all in a no project, but if I go here, you'll see that I have tons of projects. So if I go to like my PhD research project, so this is where I'm going to say I want to save the RMD file, but I don't want, so saying yes to saving the RMD file is fine. So in my PhD research project, it's a contained unit that will have all the files and starts and stops that I've done, and all of my RMD files that I've worked with. I do have some R files where I just have the raw code, where I want to keep it nice and simple, and it will have like things that I looked at but that aren't in my environment, but I can look back at them to see what was in there. I can't do anything with it because it's not actually in my environment, but I can still see that I looked at it. So projects are really nice. And you can also connect them up to GitHub, and it will sync that up there if you need to collaborate with people over GitHub. You can do pushes and pulls within RStudio.